Learning objectives E and F are going to be related to this box activity we're going to start. So let's take a look at an example to help you with your activity. In this example, a company wants to produce an open top box from a 60 centimeter by 45 centimeter piece of cardboard. So here it is, 60 by 45. They want to have the largest possible volume of this box. The picture here shows the way the cardboard will be cut and what the box will look like after it's assembled. So here is a two-dimensional look of a sheet of paper or cardboard. Here's a three-dimensional look of it as it's folded. What they want us to do is write the equation for the volume of this box. Now keep in mind this box does have a technical term. It is called a rectangular prism because it is named by the shape of the base of the actual box. Now how do you find the volume of a box or rectangular prism? Easy enough, that's going to be length times width times height. And on this, what we can see is that the length is right here, the width is right here, and we have the height. So let's just go ahead and multiply all three of those together. Now, what we have here is technically this is called three different factors or three different groups. Now, what I want us to do is actually write this in standard format and not factored format. So to think about how to get this in standard format, I first need to multiply two of these together, and then once I get that simplified, multiply this in. So let's get started by just doing this first one. It's easy enough. It's just going to be 60x minus 2x squared. And then we have 45 minus 2x. Now let's do the multiplication on this. We're going to do our complete distribution. Remember, this goes here, and then this one goes here. When we do that, here's what we're going to get in our long written out version. Is this right here. Now in standard format, I'm going to write the final equation. So we're going to put here that the velocity is equal to 4x cubed. Let's add our like terms of our x squared, so negative 200 x squared, and then plus 2700 x. So this is the volume of this rectangular prism right here. Now what they want to do is they want to fold this sheet of paper to get this prism such that this has the largest volume, that I can fill it with as much stuff as possible. How do we go about figuring out the maximum volume this box can handle? Okay, first thing I want you to look at is the equation though. What does the x and the v stand for? This v here is obviously the volume of the box, but what does the x in this equation stand for? Well, if you look at this picture, you see it right here. X is that actual height of the box. So if we can maximize this volume equation for whatever the x value is, we can figure out the maximum height for the maximum volume. Now, the easiest way to do this is to recognize this is a polynomial function. If we graph the polynomial, we are going to get a picture on the graph paper such that our x is here and the v is here. So it'll be a picture of the height of this box right here on the x-axis with relation to the volume. We want the highest volume possible. Let me show you what the graph looks like. Once you graph it and get a good window, what you're going to get is something like this. Now I'm going to tell you the hardest part of this activity is getting a good window. When it is set at negative 10 and positive 10, you don't see anything. So what you're going to want to do, some suggestions to get a good window. I would do zoom, fit, and it'll find it. And it's still not going to look that great. Once you do a zoom fit, sometimes it helps to do a zoom out. Now, if that still doesn't look good, then what I would do is just go to the window and start playing with the window values. But again, before you maybe even start these two zooms, make sure it's first at a good zoom standard, which is number 6 on the calculator zoom features. So do standard, then try a zoom fit, then zoom out and play with it to get a good window. Now let's talk about what's good and what's bad for a window. The graph paper, if you think about it, this is the x and this is v. Does it make sense to have x's being negative values? Remember, the x is the height of this box. Quadrant 2 in here makes no sense. Now, down in quadrant 3 and 4, this is the V, this is volume. It makes no sense to have negative volume. So the only relevant part of this graph is quadrant 1. So you really want to spend some good time getting a good picture. Now what this picture shows you is that as the X values or the side of the box gets larger and larger, the volume goes up. Can you see where it's maximized? Sure, it's right here. So how do you find that? You use your calculator. You're going to do second calc and find the max. Do your left bound and your right bound. When I did that, it kicked back and gave me this as the final answer. So let me write that down. That said that X was equal to 8.486. V was equal to 10,234.021. So what does that mean? Well, what it told me is the maximum volume, and on this one we are dealing with centimeters. It means I can fill that box with over 10,000 little 1 centimeter by 1 centimeter cubes. That's the biggest it can get. Well, how big does the box have to be? Well, remember the shape of this box looks something like this. This X value we found was this dimension. So I actually know one of the dimensions was this right here. Well, how do you find out what the other dimensions are? How do you know what this is and how do you know what this is? Well, we had the original formula or the original drawing. This one said take 60 minus 2x. This one said take 45 minus 2x. So do that. Put the X value into these two equations, these expressions, and you will get the complete dimensions. So based on that, the dimensions are this value, and this value. So then I could go ahead, if I needed to, I could fold my 2-dimensional sheet of cardboard into a 3-dimensional box without a lid.